You know, you probably know exactly where you are in your printing journey right now. Like, you have your FDM printer perfectly dialed in, right?
Yeah, that's sweet spot.
Yeah, exactly. You're successfully printing PLA and PPG. You're not even breaking a sweat, and your bed adhesion is just flawless. You've probably downloaded, I don't know, countless models from Printables or MakerWorld by now.
Right. You're essentially running a miniature manufacturing plant right from your desk. It feels incredibly rewarding.
It really does. It's a great place to be.
There is nothing quite like that moment. You know, when the first layer goes down perfectly and you just know, like, just from the sound of the stepper motors that the print is going to succeed.
Yeah, you've totally conquered the hardware side of the hobby.
Exactly.
But then you hit the wall. You encounter the classic maker problem. You look at your desk and realize you need a highly specific bracket, like to mount a weirdly shaped power strip to the leg of your desk.
Or a replacement part, like your vacuum cleaner drops a tiny custom plastic clip and you need a replacement right away.
Right. And you check all the repository sites and nobody has designed it yet.
Yep.
So you realize you need to make your own models, but staring at a blank digital canvas is, well, it's intimidating.
Oh, completely. That transition from being a consumer of 3D models to a creator of custom parts, I mean, it's probably the single biggest hurdle in this entire hobby.
Definitely.
The options for software are vast, and choosing the wrong path early on can lead to massive frustration. You want to build things, not fight with complicated menus for hours on end.
Which brings us to the mission for this deep dive. We are comparing the two main free modeling paths that hobbyists use for 3D printing.
Right.
We're looking at parametric CAD and Fusion 360 for precise functional parts, and we're looking at mesh sculpting in Blender for those organic flowing shapes. Okay, let's unpack this, because before we even open the software, we really have to talk about the mindset required for mechanical parts.
We absolutely do, because when you need absolute precision, you need a tool fundamentally built for engineering. And that brings us to the core philosophy of Fusion 360. It uses a parametric approach. This means your 3D model is not just a static lump of digital material.
It's more like a living thing, right?
Basically, yeah. It's a sequence of logically connected operations. Like, every line you draw and every shape you pull has named dimensions, and all of these steps are recorded sequentially in a timeline at the bottom of your screen.
So, I think about it like this. When I first started out, I messed around in Tinkercad. And Tinkercad feels very much like playing with simple wooden blocks.
Yep, the classic entry point.
Yeah. You take a cylinder, you smash it into a cube, you group them together, and boom, you have a new shape. But Fusion 360 feels entirely different. It feels like you are writing a highly dynamic recipe for a part. You're not just mashing shapes together.
That is exactly the right analogy. You are building the instructions for how the part should exist step by step. You're telling the software, hey, draw a rectangle of exactly 40 millimeters by 20 millimeters. Then you instruct it to pull that rectangle up into a box. Then you tell it to drill a hole exactly 5 millimeters from the top edge. And the beauty of that timeline is that it acts like a time machine for your design.
Right, which is huge, because I know from experience that I always measure something wrong the first time.
Oh, we all do.
Like, if I measure the hole for a screw and make it 3 millimeters, but later realize the screw is actually 4 millimeters, I don't have to start over. I just roll that timeline back to the exact moment I drew the hole, change the 3 to a 4, and the software recalculates everything going forward.
And that parametric nature goes even deeper. You can set up mathematical relationships between your dimensions.
What do you mean by that?
Well, you can tell the software that the hole diameter should always be exactly half the width of the entire bracket. So if you decide to make the bracket wider later on, the hole automatically scales up to match that mathematical rule.
Wow. But, I mean, I can hear some listeners groaning right now, thinking that jumping straight into professional engineering software is complete overkill. It sounds like you might need a degree in mechanical engineering just to make a vacuum clip.
It does sound like a lot.
Especially with all the menus and features packed into Fusion.
What's fascinating here is that for 3D printing, most Fusion 360 users only touch a tiny subset of the available tools.
Really? Just a subset?
Yeah. Specifically, you only really need to master sketch, extrude, fillet, and chamfer. You do not need to learn the advanced thermal simulation modules,
Oh, goodness.
And you don't need the complex surface modeling tools that automotive engineers use to design car panels. Just those 4 basic tools, sketch, extrude, fillet, and chamfer, will get you through the vast majority of functional parts you will ever have to print.
Okay, that does make it sound a lot more approachable. Just draw a flat shape. pull it into 3D space and smooth out the edges. And the parametric part really shines when you want to design something reusable, doesn't it?
Absolutely.
Like, I have a self-watering planter insert on my desk right now. If the designer built that parametrically, they probably defined the wall thickness as a specific locked parameter.
Yes. That planter insert is a brilliant example of why parameters matter for physical objects. Let's say you design that insert for a small desktop pot and you lock the wall thickness at 2 millimeters.
Yeah.
Later, you buy a massive pot for your living room. If you just take your original flat model and scale it up 300% in your slicer software, everything scales up, including the walls.
Oh, right.
So suddenly your 2 millimeter walls are 6 millimeters thick, which is a massive waste of filament and print time.
Or, conversely, if I try to scale a large model down to fit a tiny succulent pot, those walls scale down too.
Exactly.
They become like 0.5 millimeter thick, and my printer just produces a fragile, stringy mess that falls apart in my hands.
Right. But with Fusion 360, you avoid all of that slicer scaling nonsense. Because you used a parametric design, you just go back into your parameters menu. You type in a new number for the overall height and width to fit your new pot, but you leave the wall thickness parameter at exactly 2 millimeters.
That is so smart.
The software automatically updates the entire model, expanding the overall size while maintaining the exact wall thickness you need for structural integrity.
That level of control is incredible. But designing a perfect model on a screen is only half the battle, because FDM printing introduces very stubborn real-world physics.
Oh, gravity.
Yes, the biggest one being gravity. We can't just put plastic into thin air.
We certainly cannot. Overhangs are the great enemy of FDM printing. You know, a standard desktop printer using a 0.4 millimeter nozzle can generally handle an overhang angle of about 45 to 60 degrees without needing any messy support material underneath it.
Right.
If you design a part with a sudden 90-degree shelf sticking out, the printer will just extrude hot plastic into empty space.
And you end up with what we affectionately call the spaghetti monster.
The dreaded spaghetti monsters.
So you have to design the geometry of your part with those specific angles in mind from the very beginning. I see this debate all the time regarding the bottom edges of a print, specifically choosing between a fillet, which is a rounded sweeping edge, and a chamfer, which is a flat angled cut.
Right. From a purely aesthetic standpoint, people constantly gravitate toward fillets. A smooth, rounded corner looks highly professional, like a molded consumer product.
It looks nice, yeah.
But for the reality of 3D printing, chamfers are vastly superior, especially on any surface touching the print bed.
I have run into this exact issue.
Yeah.
If you put a rounded fillet on the bottom edge of a cube facing the bed, the very start of that curve, like right where it meets the glass or PEI sheet, is incredibly steep.
It's basically an overhang right at the start.
Exactly. It's practically horizontal for the first few layers. The nozzle has almost nothing to grip onto from the layer below it, and the plastic just curls up.
And that curling ruins the dimensional accuracy of the bottom of your part. A chamfer completely solves this.
How so?
A chamfer creates a straight, predictable angle. If you model a flat 45-degree chamfer on that bottom edge, your printer will handle it effortlessly. Every single layer steps out by a mathematically consistent amount, giving the hot plastic a solid foundation.
So no curling.
Right, you get perfect bed adhesion and a completely clean surface finish without any curling.
Okay, so Fusion 360 is clearly a powerhouse for these mechanical considerations. But let's talk about access. Professional CAD software is historically notorious for costing thousands of dollars a year.
It used to be, yes.
That's a massive barrier for someone just wanting to fix their vacuum cleaner.
The landscape has changed significantly, though. Fusion 360 runs natively on both Windows and macOS, which is a big win for accessibility. It is important to note that it's a cloud-oriented software. Your projects are calculated and saved online. Because of this, you absolutely need an Autodesk account, and you do need a stable internet connection to use it effectively. It's not an offline, standalone program.
But regarding the actual cost for a hobbyist?
This is the critical detail. Fusion 360 offers a free personal use license specifically for hobbyists, and it includes most of the features you'll ever need for 3D printing.
Are there any catches?
Well, it's not completely unlimited. It does have firm limits compared to the paid subscription. For example, you are limited to having only 10 active editable documents open at once.
Okay, 10 isn't terrible for a beginner.
Right. You also don't get access to team collaboration tools, and they lock out some of the advanced automated manufacturing features. But for designing brackets, clips, and enclosures at home, the free tier is incredibly capable.
And for listeners who want to learn those exact mechanical tools without spending 40 hours sifting through random YouTube tutorials, there are dedicated paths. Like, I noticed that Prusa Research offers a structured online course specifically in 3D modeling with Autodesk Fusion.
Oh, yeah.
It's aimed at complete beginners and costs $24.99. It seems entirely focused on the specific tools you actually need for 3D printing.
It is a great resource because it aggressively filters out the noise. When you open a CAD program, the sheer number of menus can cause analysis paralysis. A structured course just teaches you the recipe-building mindset we talked about earlier.
Here's where it gets really interesting, though. We spent all this time talking about precise brackets, mounting plates, and structural tolerances. What if our listener wants to model a tabletop gaming dragon, or a highly detailed costume mask, or a stylized planter covered in winding vines?
That's a whole different world.
Right. If I had to mathematically define every single organic bump on a dragon's snout using sketches and parameters, I would probably throw my computer out the window.
It would be an exercise in utter misery. CAD software is entirely the wrong tool for that job. When you need flowing, irregular geometry, you have to leave the strict engineering mindset behind and adopt a sculptor's approach.
Enter Blender.
Exactly. This brings us directly to Blender. Blender is fully free, open source, and it fundamentally operates differently than CAD. Instead of parameters and sketches, Blender works with a polygonal mesh.
So, not mathematical rules.
Nope. You are manipulating a surface made of thousands or even millions of triangles and quads, and you shape them just like you would shape digital clay.
I love the digital clay analogy. Moving from Fusion to Blender feels like moving from a highly rigid drafting table covered in rulers and protractors straight to getting your hands dirty on a digital potter's wheel.
It really is a vibe shift.
You stop obsessing over exactly how many millimeters wide a character's nose is, and you just take a brush tool and push and pull the geometry until it looks visually correct.
Exactly. The workflow is entirely intuitive and visual, but we have to address a major hurdle.
The interface.
Yes, the interface. When you first open Blender, the interface is incredibly dense. There are toolbars, timelines, and dozens of floating panels everywhere. It can be just as intimidating as CAD, if not more so, because the logic feels less linear.
I remember opening it for the first time, accidentally hitting a key, and suddenly my camera view was stuck upside down, looking at a gray void. How does a beginner even start moving around without panicking?
Mastering the camera is step one. In Blender, navigation is heavily mouse-driven, relying on the middle mouse button. You click and hold the middle mouse button to rotate your view, to orbit around your object.
Got it.
If you hold the Shift key plus the middle mouse button, you pan your view side to side or up and down, and you simply use the scroll wheel to zoom in and out. Getting that muscle memory down is crucial before you even attempt to sculpt.
Okay, so the middle mouse button is basically your steering wheel. Once you can actually see your digital clay, how do you go about shaping it? I know there are different workspaces you have to toggle between.
Yes, Blender relies on distinct modes depending on what action you're performing. Users frequently switch between object mode for selecting and moving the entire item around the scene, edit mode for tweaking the individual points or vertices that make up the mesh, and sculpt mode, which gives you the brushes to actually push, pull, and smooth the surface.
I've read quite a few tutorials on this, and the community sometimes throws out very rigid, absolute statements about how Blender works under the hood, like defining exactly how many modes exist or the precise mathematical makeup of a starting cube.
We actually need to be quite careful with absolute statements regarding Blender's underlying architecture. The software is vastly complex.
Right.
For instance, while some community sources might adamantly claim Blender has exactly 3 core modes, or that a simple digital cube starts with exactly 8 vertices under all conditions, the official documentation actually is not conclusive on those exact numbers.
Oh, interesting.
Yeah, the architecture changes depending on context, modifiers, and updates. So rather than getting bogged down in software theory, we should just focus on the practical tools needed for printing. And that means mastering object, edit, and sculpt modes.
That makes perfect sense. We do not need a computer science degree in mesh topology. We just want to make a printable dragon.
Exactly.
But that organic sculpting process actually introduces a massive problem for FDM printing. With CAD, the software inherently knows what is solid plastic and what is empty air. With digital clay, as I pull a long horn out of a dragon's head, I'm stretching those original polygons.
Yes, you are.
If I stretch them too far, the mesh becomes a jagged, chaotic mess of overlapping triangles. How do we get that broken mess to actually print?
That is the biggest printability hurdle in Blender by far. As you sculpt aggressively, pulling out horns or pushing in deep eye sockets, those initial triangles stretch into long, thin slivers.
And the slicer hates that.
Eventually, the mesh gets ruined, and the slicer software will not know how to read it. The most elegant solution inside Blender is a tool called voxel remesh.
I have used this, and it feels like pure magic. The way I understand it, voxel remeshing is like taking your complex, stretched out, messy sculpture and asking the software to rebuild it entirely out of tiny, perfectly uniform digital Lego bricks or voxels.
It's exactly it.
You tell Blender to run a voxel remesh at a specific resolution, say 0.5 millimeters to 1 millimeter.
That is a perfect visualization. The software drops a microscopic 3D grid over your entire object, recalculates the volume, and creates a brand new watertight skin over the shape made entirely of fresh, even polygons. It completely fixes the stretched out areas.
And it solves the overlapping geometry problem, too. Like if I sculpt a completely separate arm and just drag it so it shoves into the torso of my character, voxel remesh fuses them together, right?
It does.
It deletes all the messy interior geometry where they overlap, leaving one continuous outer shell.
It is mandatory for 3D printing complex organic shapes. But there's another hidden trap when moving from Blender to a slicer. I'm talking about scale.
Oh boy.
People will spend 20 hours meticulously sculpting a beautiful tabletop miniature. They export it, open it in their slicer, and the object imports at the size of a single bacteria, completely invisible on the build plate.
I've absolutely done that. And the fix is all about the initial setup, right? Because Blender defaults to just generic, abstract digital units, not real-world measurements like inches or millimeters.
Precisely. Before you sculpt a single thing, you must go into Blender's Scene Properties menu and set the underlying units to metric.
Okay.
Furthermore, you need to ensure the scale multiplier is set so that one Blender unit equals exactly 1 millimeter. If you miss this crucial step, the slicer receives a file with coordinate data but no real-world context, resulting in those massive sizing errors.
So locking in metric units is non-negotiable. Are there any other built-in safety nets in Blender to help ensure a model will actually survive the slicing process?
Yes. Blender includes a built-in add-on called the 3D Print Toolbox. It's disabled by default, so you do have to go into the user preferences and check a box to turn it on.
Good to know.
Once you do, it provides a dedicated panel that acts like a pre-flight checklist for your model.
I'm guessing it's looking for those microscopic tears in the mesh, you know, the things that cause a print to fail halfway through.
Exactly. It aggressively checks for critical geometry errors. It looks for non-manifold edges. A non-manifold edge is basically a hole or a tear in your digital skin.
Sounds bad.
It is. When the slicer hits a hole like that, it gets incredibly confused because it can no longer calculate what is supposed to be solid plastic on the inside versus empty space on the outside. It also checks for flipped normals.
And a flipped normal is when a polygon is accidentally facing the wrong way, right? Like the software thinks the outside of the face is pointing inward.
Yep.
When the slicer hits a flipped normal, it often just assumes that section of the model is empty air and refuses to print it entirely, leaving a weird gap in your physical part.
Spot on. The toolbox highlights those flipped normals so you can recalculate them to face outward. Finally, it checks for thin walls.
Which is huge for FDM.
It's vital. If you sculpt a flowing cape on a character, and that cape narrows down to a thickness of 0.5 millimeter, a standard 0.4 millimeter nozzle simply cannot print it reliably.
It'll just be a stringy mess.
Exactly. It requires walls to be at least 0.8 to 1.2 millimeters thick to lay down enough perimeters for structural integrity. The toolbox highlights those fragile areas so you can thicken them up with a brush before you export.
Okay, so let's say we have sculpted our dragon, we used voxel remesh to make it solid, we forced the scale to metric millimeters, and we ran the toolbox to fix all the flip normals and thin walls.
We're ready.
Now we have to get the data out of Blender and into our slicer program. This is where file formats matter.
They matter deeply. You generally have two main options for exporting. The legacy option is exporting to an STL file.
The classic.
Yeah, but STL is an ancient format originally developed around 1987. It is incredibly basic. It simply describes the outside surface geometry of your object as a dumb mesh of triangles. It carries no other information. It's ubiquitous, so every program accepts it, but it is deeply limited.
And I know the community is actively trying to move away from STL. We really should be using the alternative, which is the 3MF format.
Oh, without a doubt.
3MF is vastly superior because it actually holds metadata. It embeds the real-world scale information directly into the file, which finally ends the frustration of parts importing at the wrong size. Plus, if you're lucky enough to have a multi-material printing setup, 3MF can actually carry the color data for different parts of the mesh.
If we connect this to the bigger picture, we are looking at two incredibly powerful, entirely free paths. We have the rigid, mathematically precise engineering environment of Fusion 360 and the freeform, intuitive digital clay of Blender.
I see hobbyists get completely paralyzed here, though.
Yeah.
They try to learn both at the exact same time, which is overwhelming, or they pick the wrong tool for their specific project and just quit out of frustration.
It happens all the time.
But let me throw a controversial idea out there. Blender is completely free. It has no license tiers, no document limits, and no cloud requirements. It has a massive, passionate community. Given all that freedom, shouldn't a new hobbyist just force themselves to learn Blender and use it for absolutely everything, even brackets?
I have to strongly push back on that approach. If your only goal is a completely free, frictionless entry point just to slap basic geometric shapes together, Tinkercad already exists for that exact reason.
True.
But when you move past basic blocks, the underlying math matters. CAD is fundamentally better suited for mechanical fits. Trying to use Blender's organic, polygon-based tools to design a replacement gear that needs exact 0.1 millimeter tolerances to mesh with a motor is going to be an exercise in pure misery. You're fighting the core nature of the software.
That's a fair point. Trying to hammer a nail with a screwdriver just because the screwdriver is free doesn't make it a good idea.
Yeah.
We need a clear, practical framework to help people choose their path today. Let's lay down a definitive decision guide.
I think we can distill it down very simply, based entirely on the physical end goal of the part you're trying to hold in your hands.
All right, let's hear the breakdown.
Reach for Fusion 360 whenever your part must physically interface with the real world to tenths of a millimeter. If your design must fit an existing screw hole, if it needs to snap onto the sharp edge of a desk, if it is a custom electronics enclosure, or a replacement gear for an appliance, you use Fusion 360.
The timeline is key there.
Exactly. The parametric timeline is your safety net. It means you can easily go back and tweak those tight tolerances after a test print until the mechanical fit is absolutely perfect.
And on the flip side, the path for the artist.
Reach for Blender whenever you are modeling a tabletop figurine, a wearable costume piece, a decorative wall relief, or an organic planter. Whenever the smooth, aesthetic flow of the curves matters more than hitting an exact mathematical dimension, Blender is your undisputed tool of choice.
So what does this all mean? We've covered a massive amount of ground today, from parametric timelines and chamfer mechanics to voxel remeshing and the superiority of 3MF files. But I want you, the listener, to take concrete action on this knowledge today. Do not just listen to this deep dive and move on to the next one. Here is your specific mission for this week.
Applying the concepts immediately is the only way this knowledge sticks. A practical, constrained assignment is the best approach.
Exactly. I want you to go to the Autodesk website today, navigate their menus, and install Fusion 360 using the free personal use license. Once it is running, I want you to find a simple functional bracket that you have previously downloaded from Printables or MakerWorld, something you already printed and used.
Something familiar.
Yeah. Your mission is to rebuild that exact bracket from scratch in Fusion 360.
And the key here is strict constraints. Keep the process incredibly simple.
Keep it exceptionally simple. I only want you to use 3 tools for this entire exercise. Create a sketch to outline the base shape. Use the extrude tool to pull that sketch into a solid 3D object. And finally, use the fillet or chamfer tool to smooth out the harsh edges.
No advanced tools.
Right. Do not look at any advanced features. Just focus on feeling what it is like to use parametric, dimension-based editing to create a precise physical part.
That is a fantastic starting exercise. It completely removes the pressure of having to invent a brand new design from your imagination and allows you to focus entirely on learning the mechanical workflow of the software.
Builds that foundation.
This raises an important question, though, as you progress in your journey. Today, we have neatly separated these 2 tools into a mechanical box and an organic box. But what happens when you eventually need to design a part that demands both?
Oh, that's tricky.
Imagine you decide to design a custom flight simulator joystick or a highly specialized ergonomic handle for a woodworking tool.
Oh, that's a brilliant point, because the inside of that joystick needs absolute rigid mechanical precision to securely house the circuit boards, the switches, and the mounting screws. You need the parameters of CAD for that.
Precisely. But the outside of that same joystick needs to be a highly organic, beautifully sculpted, ergonomic grip that flows perfectly to match the contours of a human hand.
You definitely need the digital clay of Blender for that exterior.
Exactly. I want you to think about how these two entirely distinct modeling philosophies might eventually collide or beautifully complement each other in a single advanced project as your skills grow. Do you design the rigid mechanical core in CAD first, export it, and then sculpt the organic clay over it in Blender?
Or do you go the other way?
Right. Or do you sculpt a beautiful grip in Blender first, and then bring it into Fusion to precisely cut out the mechanical holes? There's an entire world of advanced, hybrid design waiting for you once you master these distinct basics.
It is a massive concept to think about, but it all starts by taking that very first step with a simple bracket. Once you do that, everything changes. You stop relying on what other people have graciously uploaded, and you finally start manufacturing exactly what you need. For the full numbers, see printerred3d.com.